The next seminar will be given by Sérgio Xavier, who will tell us about traversable wormholes and light rings.
Thank you, Carol. So first of all, I would like to thank the organizer for the opportunity to present my work here. And today I'm going to talk about this work that soon will appear in Physical Review D and was developed in collaboration with Professor Herdeiro and Professor Crispino. And in this work, we explored the light ring structure of a general class of an inter-universe wormhole. Okay? So in the first part of this presentation, I will provide the motivation behind our research. Following that, in the second part, we're going to discuss the main results of this paper, and then I will conclude with some final remarks on these results. Okay. So, as was discussed yesterday, the standard astrophysical description of these compact objects in the sky tell us that massive, dark, and compact objects are black holes. However, there are several regions to challenge this black hole picture, right? So, and consequently, becoming interesting to explore the landscape of these horizonless compact alternatives. And as we learned from Guilherme yesterday, compact objects that have light rings are called ultra-compact objects. And just a remark, here, when I say ultra-compact object, I will be referring only to horizonless alternatives, so I will not talk about black holes, okay? So, in 2017, this paper was published where the authors have proved this theory, saying that ultra-compact objects that are formed from quasi-Minkowski initial data must have at least 2 light rings, and one of these light rings must be a stable one. Well, the presence of a stable light ring in a compact configuration can introduce the potential for non-linear space-time instability, and therefore, since the stable light ring can trap and accumulate massless perturbation. So, in this another work, the authors have shown that these ultra-compact configurations, and in the presence of a stable light ring in this ultra-compact configuration, leads the ultra-compact objects either to shift away from the ultra-compact regime, and therefore losing their light rings, or they collapse to a black hole. However, both of these results here are not valid to a certain class of ultra-compact objects. They are the object that we will be interested here today. They are wormholes. So, wormholes can be, at least from a topological point of view, divided in 2 classes. So the first class is basically a connection between 2 different asymptotic regions, or if you wish, 2 different universes. And the other class is basically a bridge between 2 different locations of the same asymptotic regions. So in the work of today, we're going to be interested only in the first case, the inter-universe wormhole. And they will be described by this metric here, which represents the general class of stationary and axisymmetric inter-universe wormholes. And we choose as a radial coordinate a coordinate that covers both sides of the throat, going from one of the asymptotic regions to the another asymptotic region. And also, we impose some asymptotic flatness conditions, okay? And we'll be interested here in the light ring structure of these spacetimes, and therefore, we're gonna use a topological approach. So how is the idea? What is the idea, sorry? So the idea is to assign to each light ring a topological charge. And how do you do that? So first of all, you have to identify the light rings as critical points of this geodesic potential here. And from it, you can construct a vector field, and which is basically the normalized gradient of this 8 potential. And from this vector field, you can assign a topological charge to the light ring, basically computing how this vector field winds around a closed path that encircles the light ring. And you do this by computing this integral here, whereas W is the topological charge of the light ring, and this omega is an angle defined by this decomposition of the vector field. And this counter C here can assume any shape. The shape is not important here, as long as the integration path does not cross any light ring, okay? So here is an example of the behavior of this vector field for a static traversable wormhole. So the throat of the wormhole is located here at the L equals 0. And so here's an example of one of the counters that you can choose to compute the topological charge. And the red dots here represents the light rings of this space-time, okay? So depending on the value of the topological charge, you can have two classes of light rings. The first one is the ones that have topological charge equal to -1. They are called standard light ring, and they are basically saddle points of this effective geodesic potential. And the other class has topological charge equal +1, and are basically extrema of this effective geodesic potential. So, for instance, a stable light ring, right? So, for our case, since we are interested in a general class of inter-universe wormholes, we are not going to use any one of these counters here, but we're going to use this counter here that is basically the boundary. So it's the union of these four paths, C1, C2, C3, C4, and is the boundary of a region I that covers both sides of the wormholes, both sides of the wormhole's throats, including the throat, of course. And the idea is to extend this boundary such that after you take appropriate limit, this boundary covers the entire space-time of this general class of wormholes. And after you take this limit, you can compute the total topological charge for the entire wormhole space-time. So our job here is basically to compute the topological charge after you take this appropriate limit. The asymptotic limit that is doing this delta going to 0, and the asymptotic limit, sorry, the x limit and the asymptotic limit that you obtain, okay, by making this r going to infinity. So to compute the x limit, you can obtain it from this expression here. And what you learn from this result is that as you integrate the vector field along this path that represents the x limits, you see that the vector field is constant there. So this means that the contribution to the total topological charge of the x limit is 0, okay, because the vector field doesn't widen as you integrate along this path. And to compute the asymptotic limit, you can analyze the sign of the radial component of the vector field, and as you apply the asymptotic limit, so you go to +infinity or -infinity, right? So in one of the asymptotic regions, for instance, here at the integration path C1, you see that the radial component of the vector field has a negative component. So it means that the vector field behaves like this. And doing a similar reasoning, you can see that at the integration path C3, the vector field has a positive radial component, and therefore behave like this. But remembering that at the x limits, the vector field behave like they indicate by the red arrows, and assuming that the transition from this inward behavior to this upward behavior must be continuous, you can conclude that as you integrate this vector field in a counterclockwise direction, the vector field winds of an angle of pi in a clockwise direction, so in a negative sense. Therefore, the contribution of this path to the total topological charge is equal to -pi. So after summing all the contributions to the total topological charge for the four paths C1, C2, C3, and C4, you can conclude that the total topological charge is equal to -1. And what this means? So this means basically that these inter-universe wormholes that is basically wormholes that connect two different universes. They are stationary, axisymmetric, and asymptotically flat, either static or rotating, either symmetrical with respect to the throat or asymmetric. They must have at least one standard light ring. So this means that they are in, at least from a topological point of view, in a different class than the ultra-compact objects that I was talking at the beginning of this presentation. So to conclude, this was one of the results of this paper. So here in this talk, I only talk about the topological approach to this result, but in the paper we discussed this result from another point of view by analyzing geodesic curvature in an optical metric. And also we will prove a result showing that if the wormhole is symmetrical with respect to the throat, it must have a light ring in the throat. So that's all, and thank you for your attention.
Thank you, Sérgio. Questions?
Thank you, Sérgio, for your presentation. In the start of it, you mentioned that there are two kinds of wormholes, and you study exactly the kind of the inter-universe wormhole. But I'm asking myself if there is, how can you distinguish an inter-universe wormhole from a intra-universe wormhole mathematically? So you have an ansatz, or you have another kind of equation that you have to start to work with?
Thank you for your question, Pedro, because, so this is an interesting question, and the difference between these two kinds is only at the topological level. So, and from the, as you know, the Einstein's equations, they do not impose the topology, right? So from a geometric point of view, for instance, I don't think you can distinguish between these two kind of wormholes. For instance, if I gave you a metric of a wormhole, you cannot distinguish if it is of the inter-universe class or intra-universe wormhole class. And in fact, we don't have any exact solution for the intra-universe wormhole case. So I don't know how you could distinguish between these two kinds. And in fact, just to add, in fact, this is one of follow-ups of our work, right? We are trying to solve the light ring topological structure for the intra-universe wormhole case, and try to see if it could be different. And because if yes, okay, maybe you could distinguish the two cases somehow.
So thank you both. Any more questions?
So why is this wormhole traversable? What makes it traversable?
Okay. This was a condition that we imposed. So the traversability condition means that the causal geodesic, the new and time-alike, they do not encounter any event horizon or singularity. So we choose to work with traversable wormhole, but this was just an assumption. I don't know. Okay. But the condition is that, let me see if I put, but you can go here at the metric and impose that this guy here must be R, this metric function R, and N it must be always positive. Yes, I think it is. This is the condition for the traversability. At least you can guarantee that there are no event horizons, right? Yeah. This is for general, stationary and axisymmetric. Yes. Yes. No. I mean, yeah. If you guarantee that this guy here doesn't diverge, you don't have an event horizon, right? It's this guy. If I'm not mistaken. Yeah. Yeah. But I have other functions here. Yeah. I am assuming that this all of these functions obey this condition.
So, any more questions? So, just to clarify how this enters in your analysis, the fact that you assume that you don't have, because it looks like you are assuming that you have like a geodesic completeness, right? So, how this enters in your analysis?
So this basically alters the behavior of the vector fields that I show in a few slides. So if you have for instance, if you have an event horizon, the boundary conditions that you must the boundary condition that you use for computing the total topological chart will be different, and the vector you have to analyze how the vector field will behave at that place, for instance. So it's basically that.
So, thank you, Sérgio. Any more questions? Just a quick one, I hope.
Thank you, Sérgio, for the very nice talk. And my question has to do with Pedro's question. Can you go back to the first? The first? So, no. Yeah, so, I mean, if I want to distinguish between the two wormholes, I will first think that there are one kind of geodesic that this has, that this not has, that I can go in and go back to the same point. Can I?
Yes. Yeah, so this is a topological difference between these two guys here. So the first space-time is simply connected, which means that all closed orbits, all closed trajectories in this space-time can be contracted. Can be contracted into a point. However, this guy, the second class, the inter-universe wormhole, are multi-connectedness. So there are closed orbits that you cannot contract it to a point. So for instance, in this case, if you go from the point A to the point B, all the way around with, right, instead of, okay. So this could be a way to distinguish it, but remember that you are observer, so you have only local information. So I do not know how do you gonna use this. This information that you just say is topological information, right?
Okay, so let's thank the speaker again.